You ever see a drone just hanging in the air and think, how is it doing that? It seriously looks like it's breaking the laws of physics. But it's not magic, it's just, well, pure physics. Today, we're going to pull back the curtain on how these incredible machines conquer the sky, using some of the same core principles that professional pilots have to master. Ready? Let's dive in. All right, so let's just get right to it. The big question, why can these things fly? I mean, forget all the fancy tech for a second. The cameras, the GPS, all of it. How does a chunk of plastic and metal just float? It's not really defying gravity, It's more like it's in a perfectly balanced argument with it. And the answer, believe it or not, is actually pretty simple and kind of beautiful, really. It all boils down to this constant tug-of-war happening between four totally invisible forces. And once you get how that works, bam, you've unlocked the secret to pretty much everything that flies. Okay, so let's get into these four forces of flight. And what's so cool about this is that these aren't some special rules just for drones. Nope, the exact same principles apply to a tiny toy quadcopter and a gigantic jumbo jet. They're the universal rules of the sky. First up, the one we all know and, well, live with. Weight. It's just gravity, right? That constant, nagging pull trying to drag the drone, its batteries, its payload, everything, straight back down to the ground. It's the big boss that all the other forces have to team up against. So to fight that downward pull of weight, you obviously need an upward push. Now, on an airplane, that push is called lift, and it's created by the wings slicing through the air. But for a multi-rotor drone, well, it's a little different. Its main upward force is actually what we call thrust, coming straight from those spinning propellers. Yeah, so thrust is usually what we think of as pushing a plane forward, right? And for a drone with wings, that's exactly what it does. But for your typical quadcopter, oh man, thrust is the MVP. It's doing double duty. It's the power that lifts it off the ground, and it's also the power that moves it sideways, forwards, and backwards. For a multi-rotor, pretty much everything comes down to thrust. And last but not least, you've got drag. Think of it like air friction. You know how it's harder to walk through water than air? Same idea. As the drone shoves its way through the air pushes right back. That's drag. It's always fighting against the drone's movement. So when you see a drone just hanging there perfectly still, it means all four of these forces, weight, thrust, and drag, are in a perfect, delicate balance, an invisible stalemate. All right, so we've got the four forces down. Now let's get to the really cool part, the principles of rotorcraft flight. This is how a drone actually uses those forces. And trust me, this is where the genius-level engineering really shines. So, think about it. A quadcopter has no wings, no tail, no rudder. How in the world does it move forward? It's actually a super clever but simple trick. The brain of the drone, the flight controller, just tells the back propellers to spin a little faster, and the front ones to slow down just a tiny bit. What happens? The back gets more lift, the front gets less, and the whole drone tilts forward. And just like that, some of that upward push is now pointing forward, and off it goes. It's literally just tilting its lift to go sideways. But hold on a second. If you have four motors all spinning the same way, the drone's body would just spin wildly in the opposite direction, right? It'd be totally out of control. So here's the secret sauce: counter-rotation. Two props spin clockwise and the other two spin counterclockwise. This is huge because the rotational forces, that's called torque, they just cancel each other out perfectly. The drone stays locked in place. And you know how it turns? It intentionally messes up that balance. It'll speed up one pair of motors just a touch to create a little bit of torque and make a smooth, controlled turn. So clever.
All right, let's switch gears and talk about fixed-wing drones. These guys are a whole different beast. They fly more like a classic airplane, riding on air with wings. They give up that amazing ability to hover, but what they get in return is incredible efficiency and way, way longer flight times.
And this really breaks down the fundamental choice between the two. A rotorcraft is all about brute force, using its motors to push air down so it can go up. That's why it can hover and take off from anywhere, but man, it just chugs battery. A fixed wing is all about elegance. It uses its forward speed and wing shape to create lift, so it's way more efficient. It can even glide with the power off. The catch, it always has to be moving forward and it needs space to take off and land. It's all about trade-offs. Now, for fixed-wing pilots, there's this one big scary word they have to respect: stall. And no, it doesn't mean the engine died. An aerodynamic stall happens when the pilot pulls the nose up too high. See, the wing needs smooth airflow over it to create lift. If you tilt it up too much, increase the angle of attack, that smooth flow just breaks away from the wing. Lift disappears.
instantly, and the drone starts to fall. Knowing where that limit is and never crossing it is like rule number 1 for fixed-wing flight.
Okay, so now we're going to level up. We're getting into what really separates a casual flyer from a professional pilot. This is the stuff you have to know for serious operations. A pro understands that a drone doesn't perform the same way every single day. There are crucial factors that change how it flies, and managing them is everything.
So what are these game-changing factors? Well, first, there's the obvious one, aircraft weight. Slap on a heavy camera and your drone's going to be sluggish and the battery will drain way faster. Then there's center of gravity. If that camera is mounted off-center, the drone could become wildly unstable, almost impossible to fly straight. But the really big one, the invisible one that catches people out, air density, the actual thickness of the air itself.
And just look at these numbers. At sea level, we'll call that 100% air density. But go up to 3,000 meters, that's about 10,000 feet, and you're down to just 74% of that density. The air is literally thinner. That means for every spin, the propellers are grabbing onto less stuff. It's like trying to swim in water versus trying to swim in, mist. There's just less to work with.
So what does that actually mean for the drone? It means everything has to work way harder just to stay airborne. The motors have to spin faster, which burns way more battery and puts more stress on everything. And here's the bottom line. A mission that's a piece of cake at sea level could be completely impossible up in the mountains. Your drone that can easily lift a 5-kilo payload down low might struggle to even lift 3.5 kilos at high altitude. It's a massive performance.
And all of this leads us to the final piece of the pro pilot puzzle: calculations. I know, math. But this is the math that keeps people safe. Professionals don't just eyeball it. They use some pretty straightforward formulas to predict exactly how their drone is going to behave before it even leaves the ground.
Let's take a look at turning, specifically for a fixed-wing drone. This formula here looks a bit intimidating, but it describes a super important relationship between how fast you're going and how sharp you can turn. And understanding this isn't just for acing a test, it's about not flying into a mountainside.
So let's break that formula down. You've got R for your turning radius, G for gravity, but the one to really pay attention to is V, your speed. And see how it's squared? That's the killer. It means if you double your speed, you don't need double the room to turn, you need 4 times the room. Triple your speed, you need 9 times the room. You can see how this gets out of hand fast. If you're flying in a narrow canyon, knowing this number isn't just important, it's the difference between completing the mission and a very expensive crash.
Okay, here's another big one for fixed-wing pilots. And honestly, this one is all about planning for the worst-case scenario. If you lose power, how far can your drone glide? This isn't something you want to be guessing about when the motor cuts out. This formula is your escape plan.
And the formula is beautifully simple. Your glide distance is just your height times this magic number called the lift-to-drag ratio, or L/D. So a really sleek, efficient drone might have an L/D of, say, 15:1. That means for every 1 meter of altitude it loses, it can travel 15 meters forward. So from 100 meters up, it can glide a full 1.5 kilometers. Knowing that number tells you exactly where you can and can't make it to in an emergency. It defines your safe landing spot.
So there you have it. From the 4 basic forces to the complex calculations for performance, it all comes back to physics. It's what turns that magic of a hovering drone into understandable science. And as we start seeing drones do more and more, delivering our packages, inspecting bridges, maybe even flying us around one day, it's this deep understanding that's going to make it all possible and safe. So the real question isn't just how do they fly, but with this knowledge, what incredible new ways will we teach them to fly next?